All right, let's go ahead and get started. Any questions about due dates or anything that's coming up? Go ahead.
For the quiz one.
Yeah.
can you still turn that in on paper here? Or-
If you want. So yeah, if you want to turn it on paper, I'll take it. If you want to turn it in on Canvas, that's fine too. Totally up to you. If you want me to have a hard copy, just make sure I have it before I take off today. Doesn't have to be like right this second. There's also a web work due tonight. I think it's the 1-5. Anything else? All right, so we're in the middle of section 1.6 right now. We talked about this idea briefly, at the very end of class on Friday. This rational function. This one particular here has a limit of 1/2. So before I go beyond this, I kind of want to revisit to make sure that we're okay with the rationality of A, why this limit is 1/2 kind of on an intuitive level, and also the kinds of algebraic manipulations that we did to arrive at this 1/2. And also just to kind of warn you again, do we understand why I cannot evaluate this limit here, but why this one here is fine? What's that? Well, man, I'm kind of separating things here too, right? So why can I not evaluate a limit using this separation, but I can do it using this one? You have a mask? Thanks. So let's look at these limits here. So remember, I'm taking the limit as x goes to infinity. Let's just look at this one term here, 8x cubed. What's the limit of 8x cubed as x goes to infinity? It's just going to keep, so if I cube it and multiply by 8, it's going to get larger as well, right? It's never going to have a limit. So these limits don't exist. All the ones that are some function of x, all those limits are going to be non-real. But how about all these? As x gets really, really large, what's going to happen to 2 over x squared? It's going to get very, very small to what limit? 0. So that's why I can break this one down, but not this one. And that is why I did this thing here. Now, basically dividing the numerator and the denominator by x cubed allowed me to rewrite this in a form where I could make those conclusions. I know it was a few days ago, but is that kind of ringing a bell now? All right.
So just go by highest.
Yeah, and that's a good question. So I chose x cubed because that was the highest power of x that I had to deal with. All right, so let's kind of generalize this. So rational functions, being it's just polynomial divided by some other polynomial. So let's think about this. I want to say something in general about the horizontal asymptotes, or in other words, as x approaches infinity of f of x. So, first of all, which one of these 3 things did we just look at? Yeah, so we just looked at n equals n, right? So what did that limit have to do with our, maybe we should go back and look at it. So our limit here ended up being 1/2, right? How was that related to any of the coefficients of the polynomials we started with?
Related to the coefficients of the one that has the biggest power.
Right, so we call that the leading term. It's not always the first one, it's just the one on the largest power of x. So the limit ended up being essentially 8 over 16. Not a coincidence there. So if we generalize that for any rational function where the powers are equal, we can say the limit is equal to this. A sub n over b sub n. Basically, whatever the leading term of the numerator is divided by the leading term of the denominator. What's going to happen to a function that looks like this if the largest power in the numerator is bigger than the largest power in the denominator. Which is going to grow faster, the numerator or the denominator? The numerator. So if the numerator is going to grow faster than the denominator, what's going to happen to the overall function as x gets very, very big? It's just going to get bigger and bigger and bigger, right? So no horizontal asymptote. Because as basically as I graphically speaking, as I move to the right, the graph will just keep getting either further upward or further downward. What about if the power in the numerator is less than the power in the denominator? Which one's going to grow faster this time, numerator or denominator? So if the denominator is growing faster and I make that division, what's going to happen to the overall function? Smaller and smaller and smaller to zero, right? So this is going to have an asymptote at y equals 0.
Like where is it? A and x to the power of n, like the. I'm confused on what.
Basically what n is, so maybe I'll lay this next to a concrete example.
Yeah.
Does anybody have handy in their notes what the last function we looked at was? 8x cubed.
Plus 2x squared plus 1 over 16x cubed minus 147.
Thank you. So in this case, what are n and m? Actually, n and m are both 3. So basically, what n and m represent up here, whatever the highest power of the exponent are. For all those a terms, the a sub 0, a sub 1, all the way up to a sub n, those are coefficients. And they're just, the subscript just tells you basically where those coefficients live. What power of x are they being multiplied by? So n and m are both 3. But what is a sub 3 and b sub 3?
Oh, a sub 3 is 2.
A sub 3 is not 2. Basically, the a sub 3 and b sub 3 are coefficients. So this one's 8, this one's 16. A sub 2 and b sub 2. A sub 2 is 2. B sub 2 is 0, it doesn't exist. And so
What is the substrate?
the substrate just tells me that instead of me calling all the different coefficients A and B and C, like I can just call them all A sub. Like if I said, for example, A sub 10, you know that that's going to be the number multiplied by x to the 10. So it's just an easier way to organize where they actually end up. But if you're not used to this notation, it's probably very cryptic right now. Any questions about how these 3 ideas work, though? Basically, we can kind of pluck out these asymptotes just based on how these powers are related to one another. Any questions before we move on? So I want to find how many horizontal asymptotes for the following function. Is this a rational function? Is it a polynomial divided by a polynomial? It's not. So that square root messes everything up. So I can't quite treat everything like I just did with polynomials, but the good news is I can still do this a similar manipulation to what I just did. Let's start with the denominator. What's the highest power of x in the denominator? X to the first, right? What's the highest power of x in the numerator? It's 2, but it's under a square root, right? So here's what I'm going to do. I'm going to divide this by x over x. And what that's going to make the, actually, I shouldn't put that there. Limit as basically, and remember, I kind of blew past this, but if we're looking for horizontal asymptotes, remember, we're looking for what happens when x gets very large or very small. So I'm going to multiply top and bottom here, numerator and denominator by 1 over x. And with the denominator, it's probably a lot more clear what happens. The denominator is going to become 5 minus 11 over x. With the numerator, it's probably not as clear. So I'm going to write something down and we can talk about whether or not you believe me. So I'm just going to recreate the numerator as is. I'm going to multiply it by the square root of 1 over x squared. Go ahead. By 1 over x, yeah.
How come it didn't change the numerator?
Well, I mean, I just haven't simplified it yet. So one thing I want to make sure everyone's okay with before I go on is, are we okay that 1 over x is the same thing as the square root of 1 over x squared? I mean, they're equivalent things. So I write it like that because that helps me do this. Now I have 2 different expressions under a square root. I might as well just combine them. So this is going to be the square root of 1 over x squared times 3x squared plus 7x plus 1. All over 5 minus 11 over x. And from here I can make this simplification. Three plus 7 over x plus 1 over x squared. All over 5 minus 11 over x. Any questions there? Any thoughts about how to simplify this further now that we are where we are? Can we use any of those limit laws that we've used in the past? Let's look at the denominator. If I just try to take the denominator and let x go to infinity, what's the denominator going to go to? I heard an infinity and I heard a 5. So let's break it down into pieces. 5's a constant, right? So as x goes to infinity, 5 is going to remain 5. What is 1 over x going to, is it 1 over x? 11 over x. What's 11 over x going to do as x goes to infinity? It gets very large. Gets smaller and smaller and smaller, trending towards what? To 0. So the denominator is going to go to 5. So that limit exists. Now, if we can convince ourselves the limit of the numerator exists, then we can absolutely break them apart. 3 is a constant, so that's not going to get affected. What's going to happen to 7 over x as x gets very large? Go to 0. What about 1 over x squared? Right. So because of that, I can say this. This is equal to the square root of 3 over 5. Any questions here? Go ahead. So, I mean, and that's, I'm glad you brought that up. I mean, if you kind of use the, you know, if we understand that essentially the highest power in the numerator is x, or the highest power of x in the numerator is 1, same is true in the denominator, you can kind of just take the leading coefficients again, and you're going to get to the same place. The reason I'm trying not to emphasize that too much is because you're eventually going to look at functions where that rationale will get you in a lot of trouble. And I'm not going to jump too far ahead and show you one of those right now, but that can happen. But yeah, for this type of thing, I mean, and that's one of the things that I think is really valuable about when you're looking for limits is it's great to have suspicions and like hypothesis about why you're going to end up. But then make sure you can actually, you know, justify it. I mean, that argument about what happens to they're looking at the leading powers in the numerator denominator is fine for like giving yourself an idea. but it's not a very strong argument like this is. That makes sense? Okay, any questions on here, how we got radical 3/5? Okay. How about this one? Any ideas here? What do you want to look at first? X? Okay, so bottom line, I mean, let's start at the beginning. What do we want X to do? What was like the limit we care about? What do we want X to do? We want to what, sorry?
You want to like go towards how we have to find something?
Well, we don't necessarily need it to be undefined. I mean, it will not be defined just because infinity is not a number. But, you know, we're kind of looking at limits as this dynamic thing, this change in X. So what change in X specifically do we want to see? We want X to get arbitrarily large. So let's go from there. So kind of write a verbal description. X gets arbitrarily large. So let's go beyond that. As X gets arbitrarily large, you know, what's that going to affect? What's the next thing that we should look at that behavior is in effect? Isabel?
I bet it's 1 over X, and that can get really small.
Really small, does it going to trend to a limit, or is it just going to keep getting smaller and smaller?
Trend to-
Then the trend towards 0, right? So because of that, X gets arbitrarily large, that means 1 over X goes to 0. Maybe I should pause there. Are we okay with that link? Go ahead. Oh, it's the final answer. We're building up to it. So we know that based on the notation I've given you, I want X to get really large. If X is really large, 1 divided by X will decrease to 0, or have a limit of 0. Now that we understand that, what do we have to look at? So if the inside of basically the argument to this cosine, if the input to this cosine function is going to get closer and closer to 0, then can we say something now about this limit? Basically, I'm going to put a new limit here. The limit as y approaches 0 of cosine of y. Are we okay with me writing it like that? Am I answering the same question that I started with? So the first thing I asked you was, okay, as some variable X gets larger and larger, that's just going to make the input to this cosine function get smaller and smaller, approaching but never reaching 0. So I'm also asking, what's the limit as y approaches 0 of cosine of y? One thing I've told you about the trig functions is they're continuous everywhere they're defined, right? Is cosine defined where y equals 0? It is. So this right here is as simple as me asking this. I shouldn't say simple because we took a long way to get there, but if I know what cosine of 0 is, I'm done. And while we're at this, I'll remind you of one of our limit laws we talked about. The limit as x approaches a of f of g of x is equal to this. The function is going to look kind of weird, but that's okay. And this is basically what we did. Instead of looking at the limit I actually asked you for, we looked at the limit of the quote unquote inner function. We didn't really directly look at the limit as x goes to infinity of cosine of 1 over x. we started by looking at the limit of 1/x as x goes to infinity. So we've talked a lot about breaking limits down into their sums and differences and quotients and stuff like that. Combination of functions is also a really valuable way to break things down. Any questions there? All right, how about this one? Any thoughts here? I see some confused looks, which I think I like. What suspicions do you have? As x gets really, really large, what's cosine of x going to do? Is it going to get larger and larger? Think about what the cosine function does as x changes. So I see some. It just goes up and down, right? I mean, it just goes. I mean, and this is one of the. It's kind of weird to think of because everything we've talked about, or not everything, but a lot of things we've talked about so far, if the limit doesn't exist, that we're kind of used to thinking, oh, it gets really large or it gets really, really small. But in this case, as x gets, if you just let x continue to grow, you probably have a graph of cosine in your head, or you could probably recreate it. But think about what that cosine function does. Does the limit exist? Why not? Not that it's continuous. It's not approaching a single value. So that is the only way for a limit to exist if it's a real number, a single real number. Is this function here going to have a minimum y value?
Yeah.
What is it?
-1.
Is it going to have a maximum? 1. But that does not mean the function's ever going to settle in on anything in there. It's just going to oscillate indefinitely between -1 and 1. So because of that, what can I say about this limit? That's all I can say. I can't say infinity. I can't say negative infinity. I can't see the limit somewhere between -1 and 1 because it's not. Just because the function's always inside that range doesn't mean that a limit exists.
What is the last function? That oscillator on 0 though?
It oscillates around 0, but the large, and that's a really good observation. It will reach 0 an infinite number of times. It will never like settle in on 0 completely, but the larger x gets, like the shorter like the oscillations will get. Those of you who are engineering class, have you heard of the concept of damping or dampening? Not yet. Okay. And basically what a damped oscillation is it's something that, has this period to it, but the damping means that the amplitude decreases. And that's really what's happening with cosine of 1/x. The amplitude will always decrease. So because of that, I can make my function, kind of always be as like within so much of 0. I can make that as small as I want. So yeah, that is why the last one has a limit, but this one will not. I'm not damping it. Anything else? Or I think that is it for. Oh no. Oh yeah, here's one I wanted to. So limit laws. Let's just break this thing up. I'm going to break this up into this. The limit as x approaches infinity of x cubed minus the limit as x approaches infinity of x squared. What's going to happen to x cubed as x goes closer and closer to infinity? It's going to be infinity, right? What about x squared? How do we feel about that? Is what I did okay?
Something minus itself is there.
If you were to graph this, where's it going to be 0? So it's going to be something like this. So as x gets really, really big, this is just going to get, as the graph goes to the right, it's going to go up without bound, right? So I lied to you somewhere. Either that graph is nonsense or this is nonsense. Which one is it? The math, what did I do? What did I do that was wrong with the math? I'm treating infinity like it's a real number, which is wildly illegal. Also, I use limit laws when I just can't use them. Why can't I use the limit laws there to break that thing down into 2 separate functions? You're gonna get sick of me asking this question, but this is why I need to.
Is it because it's not a numerator denominator?
No, that's fine. I mean, I can break it down even if that's not the case. What is the limit as x approaches infinity of x cubed?
This would be infinity.
They're infinity. Do they exist?
No.
Can't use the limit laws. So only use limit laws if individual limits exist.
Would there be some cases where you would only know if they exist if you use the law?
I mean, if you
Like for like a rational function, you wouldn't know if the limit exists and you like. Okay.
well, I mean, that's kind of your test. But if they don't exist, then you know you can't. You got to try something else. And also, Isabel had a good point. You can't treat infinity like it's a number. It's not a thing you can get your hands on. You can't have an infinite. You can't have an infinity quantity of something. Doesn't make sense. So another caution on. I think it just at this level. I mean, it's so tempting. Oh, I have these rules. I'm just going to use them whenever something looks familiar. Really, you got to make sure that those rules are available to you. Oh, I don't want to stop sharing.
So would the real answer also be DME there?
Let me pull it back. And let me share because for some reason, thought I need to shut that. In this case, the real answer, I mean, the limit does not exist. We can also say the limit's infinity. Because, you know, that graph, I did not lie to you with the graph. As x gets closer and closer to, or as x gets larger and larger, y gets larger and larger. All right, that is all for chapter 1. Chapter 2, we're going to get into the idea of derivatives, which we've been kind of laying the foundations for, but now we're going to really find what they are. All right, so we've talked about this thing before. I just drop a rock off no, don't throw it, just let it free fall. The speed that the distance the rock covers over time is given by that function. I want to find the average speed of the rock over these, 4 different windows. So I think the question I asked you, the first thing I asked you on the first day was, how would I find the speed of this rock at the instant in time at 5 seconds? So I have these 4 different intervals here that have 5 seconds as the right endpoint. I think we figured out what the first 2 were. But let's just kind of catch up because I don't remember what the numbers were. The average speed. If I want to find the average speed, what I'm really doing is finding my total distance. And dividing it by my total time. which on the day we recognize as a slope calculation. I'm gonna guess, because I think I remember this came out to like 24.5 meters per second. We should probably verify before I go too far. Yeah. All right, so if I just look at the whole interval, time equals 0 to time equals 5 seconds, I get that speed of 24.5 meters per second. What if I just look at the last second? So if I just look at that last second, how would I calculate that average speed?
Speed at 4 and then speed at minus speed at 5.
Well, so, and that's kind of one of the unfortunate things about using the letter S here. The S actually is short for distance for. I can't remember what language, it comes from I think they come from the French translation of these words. So S of 5 minus S of 4 over 5 minus 4. So we're gonna have 122.5 minus whatever 4.9 times 16 is. 78.5
0.4.
all over 1. So that is 24.1. Okay, that's. So, and I think we even said on day one, seems like a long time ago, but that whatever estimate we came up with for from 0 to 5 is going to be an underestimate. And if we shorten it to 4 to 5, we get a larger estimate for speed. Let's skip ahead and do 4.99 minus, or yeah, the last hundredth of a second around where I care about. So S of 5 minus S of 4.99 all over 5 minus 4.99. All right, all told, I'm getting 48.95. But are any of these things the actual speed at 5 seconds? So what does this remind you of here? I have, this interval right here is 5 seconds long. This is 1 second long, a tenth of a second, a hundredth of a second. What does this remind you of that we've kind of been doing the last couple of weeks? What's that? So what are we limiting? Like, what are we trying to limit here? As what approaches 5?
Yeah.
Well, I mean, I've kind of done that, right? I mean, for all of these, that upper, so for all these, the upper limit of the interval is constant, right? So what am I trying to do with the lower limit?
Approach the upper limit.
I'm trying to get it to approach the, so I can look at this as a couple different ways. The limit as t, I'm going to call it t0 to the initial time as that approaches 5. It would be really, really great if I could take the slope of this function using only 1 point, right? Is that possible using the tools you have now? No, because that divides by 0. That's a problem. Okay, so t. Sorry, I guess it's not S of t, it's S of t1 minus S of t0 over t1 minus t0. But yeah, if I could really get, so t sub 1 is equal to 5. If I could get t1 and t0 to both be 5 and actually get a number off of that, that'd be perfect. I would be able to get the exact speed. That is not something you can do with the tools you have now, but that's something we're building up to. Are we okay on the rationale here? What the goal and what the goal and how we're trying to accomplish are. All right, so I want to look at a graphical representation of what we're doing here. We're talking about the idea of two different things here, graphically speaking, a secant line versus a tangent line. Has anyone ever heard that term tangent in this context before? So not like the trig tangent function, that kind of thing, but what does it mean for a line to be tangent to a curve or a circle or something else? So you've probably seen this in geometry where you have a circle, then you have a tangent. It's called a tangent because it only touches the circle at one place. Doesn't have to be a circle, it can be anything. So let's say the point I care about is, right here. I would love to be able to calculate this slope. Because that's the tangent line, that's the slope of the curve at that point only. I don't have a mathematical way to do that, so what I really have to resort to is this. I take some other point, kind of close to it, connect those with a straight line, and find the slope of that. I can do better than that. I can get as close as I want, right? So if I make points closer and closer and closer to each other, I can get better and better estimates, but there's still error. So really what I'm trying to do is I'm, again, trying to take advantage of this new tool called a limit, so I can put those points on top of each other. So here is what a derivative is. And this is going to look very similar to what we just did, especially that top one. But here's basically what we're doing. Let's focus on the right-hand side of this thing first. This quotient right here, what does this calculation remind you of? That's a slope calculation, right? I'm taking a difference in y values, dividing by the corresponding difference in x values. And I think this looks a lot like what we just wrote down. As x approaches a, I would love for these 2 points to be the same, these two x values to be equal. So that's what the limit sort of allows me to do. I can't get there, but I can get as close as I want to. So because of that, I can use this new idea called a limit.
Is that f of n?
So yeah, and so the reason I was focusing on the right-hand side is first because this contains stuff you've seen. This right here, the way you read this is f prime. And that prime, that apostrophe, what that signifies in this context is if I have a function f and a function f prime is implied to be the derivative of f. So if the word derivative is thrown you right now, I mean, it should, we haven't really, this is the first we're talking about it. We'll talk more about what that term means and, all the different power that it has. This right here is essentially the same. So in my top formulation here, I have two x values. One's called a, one's called x. In this one here, I have two x values. I really care about what's happening at x equals a. H is the distance between a and some other place because I can't just have my 2 points on top of each other. In that case, what does h represent? Yeah. Basically, it's h is how far apart those x values are. So does it make sense that I want to take limit as h goes to 0? I want those x values to be, I want to make them approach each other. So both very common ways to calculate this. What does this thing do? The derivative of f prime of a gives the slope of the tangent line at this point, a, f of a. And really, what I really want is, this tangent line is kind of just a graphical thing to kind of help us visualize it. What it really gives us is the slope of the function. It just seems silly to talk about the slope of things that aren't straight lines, but that's really what a derivative allows us to do. Also seems strange to talk about the slope of something only talking about one location, but that's why this exists.
So the derivative is the slope over, is like the slope over.
I mean, so let's talk about this next bullet here. It also gives the instantaneous rate of change. So derivative is a very fundamental thing in calculus and it has a lot of different applications. So when I talk about slope of a tangent line, I'm really talking about, I mean, that's kind of a inherently graphical thing. When you're talking about slope, it's kind of a geometric thing. When you're talking about instantaneous rate of change, it doesn't necessarily involve a graph. Maybe I'm talking about, what's the example we've been using since the first day is, if I'm dropping a rock and I know its distance, I can figure out its distance whenever I want, but not necessarily its speed. But now that I'm introducing this, I'll be able to do that too. So it also gives the instantaneous rate of change of f at x equals a. So now, because of derivatives, now do I not only know what value the function has at a point, I can tell you basically how rapidly it's changing around that point. There are cases when I want to know both. So any questions so far? And I recognize this is one of those things where you might not even know what questions to ask until we get a little deeper. So this rate of change can be applied to any pair of related quantities. So really common one, especially considering most of your engineering majors, is wanting to know the rate of change of something over time. So the speed of something, the acceleration of something, the flow rate of water through a pipe or electric current through a wire, things like that. So I want to find the equation to the tangent line at this curve, y equals negative x squared, f3 negative 9. So just to help us kind of ground this in something familiar, let's draw this function, downward facing parabola, and I care about the point (3, negative 9). So a tangent is going to look something like so if I find the equation of this tangent line, what should I expect of the slope? It's going to be negative. Is it going to be steeper than 1, shallower than 1? What do you think? It's going to be, so I'm expecting something negative, less than negative. Sorry, that's something less than negative 1. So let's make sure we can get there. So I want to find the equation of the tangent line. If you want to find the equation of any line, you need some data. You need an x and a y location, which I've given you. I also need a slope or a y-intercept. So we're talking about derivatives, so we kind of have a method to get to that slope. So that's what I'm going to do here. The limit. So I'm going to say this. One of the ways you can think about derivative is the slope of a tangent line. So let's use this limit. I'm going to use the second flavor that I gave you. The limit is h approaches 0 of this thing here. F of 3 plus h minus f of 3 all over h. So I'm taking a derivative at a point. The point I care about in particular has an x value of 3. All right, so let's go a little further. What is f of 3 plus h based on this current situation? Maybe we should ask this, what is f of x?
Negative x squared.
negative x squared. Yep. So, so the derivative is, let's just talk about in terms of tangent lines and slopes. If I want to use the derivative to find the slope of a tangent line, there has to be some function that I'm interested in. So in this case, I'm interested in this parabola, y equals negative x squared. So because of that, I'm going to use this function f of x equals negative x squared. If that's what our function is, then what is f of 3 plus h? Or maybe let's start with f of 3. What's f of 3? How'd you get negative 9? Right. Well, I mean, from the point, right? But okay, so maybe I'll ask you this. What is f of 5? How'd you get that? You just substitute, right? So if that's how you can use a function like that for anything, it doesn't have to be a known number. So based on that, what is f of 3 plus h? We okay with that? F of 5 is negative 5 squared. F of 10 is negative 10 squared. F of 3 plus h is negative 3 plus h squared. F of 3, sounds like we're okay with that. Either that is just negative 9 all over h. Is this a rational function? Yeah. Is it defined at h equals 0? This one's not, so we got to go a little further. So I'm going to go ahead and expand this. I'm going to get negative 9 minus 6h minus h squared plus 9 all over h. What are we noticing? Something very convenient happened. What's that? I can. How come? I can't. I am allowed to now. But what was the convenient thing that happened that allows me to do that? That's true.
There's an h squared right there. So h squared divided by h is h.
Right, but for example, what if this negative 9 wasn't here? I wouldn't be able to, I would still have a problem. So the thing that I really like that happened is this. Because that allows me to divide by h without actually. So for example, look at this. If I have,
So the terms about the variable.
12h plus 7 over h, for example. You can divide that and you still get this, 12 plus 7 over h. If I were to take a limit there, I'd still be stuck. But because all my constants annihilated each other, now I can make that, now I can do this division. So this right here ends up being the limit as h approaches 0 of negative 6 minus h. Can I evaluate that limit? What's that limit? Negative 6. So that kind of matches our suspicion. We thought that our slope was going to be negative and that it was going to be much steeper than negative 1. So we got the slope of the tangent line. It's exactly negative 6. So the slope of this parabola at that single point is negative 6. Let's go ahead and finish it up. Can I use that to find the full equation of this straight line? Do I have enough information to find the equation of a straight line here? Remember this thing, right? Do I have a y value? Yeah, negative 9. Do I have an m value? Yep, just got it. Do I have an x value? Yep, so that's, I have enough to get the missing piece. So negative 9 equals -6 times 3 plus b. So that gives me b equals 9. Okay. So my tangent line here is y equals -6x plus 9. So something I don't quite have time to do for you, but if you wanted to do this in Desmos, if you graph y equals -x squared and y equals -6x plus 9, you will get a line that actually touches that curve at one point, like I tried to do. But now, based on using this derivative tool, we now can find the slope of many different types of functions using only one point. Any questions?
Is that a b equals 9 bottom?
B equals 9, yeah. Yeah, let's do the y-intercept of that straight line. So if I were to follow this line backwards and to the left, this point right here, gosh, why can't I line this up? That point right there would be 0, 9. All right, that is past 3:20, and we'll go ahead and stop here. I'll see you all next time. See you.